During our last video, I introduced you to carboxylic acid derivatives. And if you remember, a carboxylic acid derivative is a compound where you have a carbon with a +3 oxidation state. So this carbon right here would have a +3 oxidation state, and the defining characteristic is some sort of electron withdrawing group coming off of a carbonyl. We saw that nitriles are one exception to that, but even with nitriles, you have a +3 oxidation state on a carbon. All right, so let's take a look at these functional groups one more time, and I'm just going to abbreviate functional groups as FG, and we'll draw them out. So we've got acid halides, we've got anhydrides that look like this, we've got esters, we've got amides, and then we also have nitriles. But in each of these, we have this electron withdrawing group coming off of the end, and we have a central carbonyl carbon with a +3 oxidation state. All right, so if we think about the electron withdrawing group that's attached, we can kind of consider them almost like leaving groups. So in the first example, if this were a leaving group, it'd be Cl-. For the anhydride, the leaving group would be a carboxylate anion. For esters, it would be an alkoxide. And for amides, it would be some sort of nitrogen with a negative charge. All right, and if we think about the leaving group ability of each of these, you can imagine that halides are really good leaving groups. They were the ones we saw in SN2 reactions. And so in general, these are better leaving groups as we go up this column. And in fact, we can actually see this by comparing the pKa of the conjugate acid of the leaving groups. So let's take a look. The pKa of the conjugate acid let's make a list. So the conjugate acid for Cl- would just be HCl. And that has a pKa of about -8. So you can tell that chloride is really, really stable on its own, which makes it a good leaving group. The next one, we would have something like a carboxylic acid, which would have a pKa typically of about 5. And you can see it's definitely not as good of a leaving group as chloride, but yeah, it's decent. And then the next one, we would have an alcohol. And alcohols typically have a pKa of about 15. So again, definitely not as good of a leaving group as either of these first two, but decent enough where it can fall off under certain circumstances. And then the last one really isn't the greatest leaving group, but we can still compare it to the others, and we can see that the pKa of the conjugate acid is about 38. So it is really important to remember that chloride, when it's attached to some sort of carbonyl compound, is really happy when it falls off. Where something like an NH2 group, it's not very happy when it falls off. All right, so what I want to do in this next section is focus on the reactivity of our acid halides, since they're our most reactive carbonyl derivative. So the first thing I want to cover is how to prepare acid halides. And I want to start out by looking at the overall reaction, and then we'll get into the mechanism after that. So the overall reaction for converting a carboxylic acid to something like an acid chloride requires the use of SOCl2. In fact, this is the same reagent that is used to convert alcohols to chloride. So in this case, it kind of makes sense that we're going to convert this OH group into a chlorine. All right, the byproducts of this reaction are going to be sulfur dioxide gas, and this will bubble out of solution, and then we'll also generate some hydrochloric acid as a byproduct. So let's take a look at the mechanism here. And the mechanism is a little bit steppy, a little bit confusing, but we'll go through it fairly slowly. And if we have a carboxylic acid, it's going to react with this super strong electrophile. That's the thionyl chloride. And what happens is this lone pair can be delocalized down and have resonance here, which means that this top oxygen is partially negative, right? And if it's partially negative, that means that it can attack an electrophile like thionyl chloride and kick electrons all the way up to that oxygen. So let's take a look at this next intermediate. So the oxygen down here now has a double bond. The oxygen over here is attached to the sulfur, and the sulfur still has 2 chlorines attached onto it. All right, in the next step, we can kick off one of these chlorines. So let's go ahead and draw this next intermediate down here. This oxygen still has its hydrogen, so it's got a positive charge, but now we've got a chlorine that fell off. So in this step, the key feature is we need to eject off a chlorine like this. So that's our leaving group that got kicked off in the first step. But chloride with the negative charge is actually a decent nucleophile. So in this next step, it can actually attack into the CO double bond. And the reason it'll do this is it's super electrophilic because this other oxygen right here has a positive charge. So we can go ahead, attack that carbon, and kick electrons all the way up to that oxygen. So let's go ahead and draw this intermediate. And there we go. So now we're at this neutral organic intermediate, and it's quite unstable at this point. The reason being is that this whole chunk right here is going to act as a leaving group. So what I'm going to do is actually change colors, and I'm just going to say that this can act as a leaving group. And I'll show you why. These lone pairs on this oxygen, if they clamp down, can kick off this portion all in one step. So this entire portion right here is going to become SO2 gas, and then this portion right here is going to become the Cl- that's kicked off. So let's take a look at what happens in this last step. In this last step, we're still going to have an oxygen with a proton. In this case, it's this oxygen right here that is now in this position. I've just kind of rotated it around. We still have our chlorine attached, but now we've formed SO2. That's our gas. And like I said, that's the area that I've highlighted in yellow. And we've also generated Cl-. So in this last step, all we need to do is a proton transfer where this chloride can grab this proton. And like I said, the chloride is actually highlighted in green above. So that's going to act as our really weak base. And we'll get our acid chloride plus SO2 gas, that's our sulfur dioxide, and now we'll have our HCl. So we do generate HCl as a byproduct, which means we can't do this as easily if we have really acid-sensitive functional groups elsewhere in our compound, but it works well for simple acid halides. All right, so it's fairly steppy, but that's the main method that's shown in the Klein textbook for producing acid halides. There's other techniques in other textbooks, but we're going to stick with what's shown in the Klein textbook. All right, so now let's jump into the reactivity of acid halides. And like I said, acid halides are the most reactive of the carboxylic acid derivatives. So the first one I want to do is really simple. It's just hydrolysis. And hydrolysis basically just means water is going to break it apart, right? So let's say we have an acid halide and we have water around. Water is a pretty weak nucleophile, but the acid halide over here is such a strong electrophile, it'll actually react with water. So in this case, water will attack in, and kick up electrons onto that oxygen. It is important to remember that every time you show these reactions, you need to show a tetrahedral intermediate. So in this case, it doesn't do an SN2 reaction where it kicks off chloride. Instead, we form this tetrahedron, and then this negative charge will clamp down, kick off our chlorine, and we're almost done now. However, our final product isn't neutral, so we're just going to go ahead and write minus H plus so that we can go straight to our carboxylic acid. So the byproduct of this reaction is going to be HCl, so it's generated there. And if we wanted to, we could even be more careful, and we could say this is actually going to be generated by the Cl grabbing one of these protons off of the end. And then if we wanted to go back to our starting material, we could by doing the exact same reaction mechanism that I showed above. So really we could go to the carboxylic acid or the carboxylic acid to the acid halide. All right, the interesting thing is a lot of tear gases are actually things like acid halides because it will react with the moisture in your eyes and in your lungs to create a small amount of HCl and carboxylic acid, which is quite irritating. So this is commonly what's used in things like tear gas that they fire into riots. So it's pretty nasty stuff, not stuff you want to breathe in. It will even react with the moisture in the air over time, so you have to keep it under dry and hydrous conditions. All right, so that's the first one, is hydrolysis. Pretty straightforward. Let's take a look at something called alcohololysis. And as you can imagine, this is going to be pretty similar. So if you have an acid halide, but instead of water you use some sort of alcohol, you can get a reaction where you can form a new ester. However, unlike the reaction with water, you actually need a little bit of help in the form of a base in order for this reaction to occur. So in order to do this reaction, you normally add some sort of base like pyridine. And this is just going to be a non-nucleophilic base. You don't want a competing reaction. With water, we don't need an additional base, but anytime you're doing a reaction like this one, you do typically need a base, especially to facilitate deprotonation at the last step. In addition, we've got another one that's pretty similar, using amines. And with amines, the same idea is true, but with one little trick. So in this example, let's say that we've got this primary amine. Well, in this case, amines are bases themselves, so all we need to use is excess of our amine. We don't need to add in any pyridine. So let's make a note here. It acts as its own base. And when we do this, we can create a new amide bond. So we've created a new functional group over here, and we've interconverted our acid chloride to our amide. As you can imagine, this works with a variety of different amines. So let's take a look at what happens if we use a secondary amine. So that's where we have R2NH, meaning the nitrogen's bonded to two carbons. Same thing's true here. It will act as its own base. And we can go ahead and we can make an amide that is more substituted. So you can use this to make a wide variety of different amides. The cool feature is the amines always act as its own base. This is a pretty roundabout way to making amides. In more modern organic chemistry, there are much more efficient techniques that are more gentle than using something like an acid halide as a starting material. But for right now, this is a pretty good technique that's provided in our textbook. All right, let's take a look at a few more reactions. The next one is going to be a reduction reaction. Let me change my colors here. And let's consider this. Let's say we have an acid halide, and we want to get to something like a primary alcohol. Well, in this case, it looks pretty similar to a reaction we saw last term, where we're just trying to reduce this CO double bond. And if you recall, we need a strong reducing agent to do that. So in this case, we could use LiAlH4, that's lithium aluminum hydride, in excess, followed by water workup. So in this case, lithium aluminum hydride is really just a source of hydride, H-, that's being carried around by aluminum. So we can go ahead and think about it this way, where this hydride, meaning this entire H- group, is going to attack in and kick up electrons onto that oxygen. As you can imagine, in this next step, all we need is to clamp down and kick off our chlorine. However, we're not done yet. We still have excess lithium aluminum hydride. And it's always going to overshoot, meaning if we have excess hydride, it's going to attack this aldehyde intermediate to give us a compound that is now reduced a second time. All right, and then in this last step, all we need to do is have this react with some sort of weak acid, like water, in order to protonate the alkoxide to give us our primary alcohol. It's interesting though. It is hard to stop here using LiAlH4, excuse me. So hard to stop here if using lithium aluminum hydride. So then the question is, well, what if we really just want to stop at the aldehyde? We don't want to overshoot. Well, one option would be to use something that's more gentle. However, that doesn't actually work very well. So if we can't use a gentle reducing agent, maybe we just make it more bulky. So that's exactly what we do. So to stop at the aldehyde, you must use a bulky reagent. All right, and I'll show you what that looks like. In fact, it's quite bulky. It's got these terbutoxy groups attached to aluminum, and each of those terbutoxy groups is huge relative to a normal hydride. And then the last position still has that hydride installed. In addition, we always want to include our countercation. This whole reagent is called lithium tri-terbutoxy aluminum hydride. And like I said, it's so sterically hindered, it won't reduce the aldehyde. It's too crowded to actually reach into the aldehyde. So we'll make a note. However, it is reactive enough to still react with the acid chloride in the beginning. One thing I did want to note was that this name is an absolute mouthful, so it tends to get abbreviated a number of different ways. So, one way of abbreviating it is LIALOTBU3H. So that's another way of abbreviating this. However, sometimes in the textbook or in other textbooks, you may see it written out this way. And really what they're doing here is they're using R as a placeholder for a tert-butyl group. So usually it's a tert-butyl group, but sometimes there are other bulky groups that can be used. So I'll just write R equals a tert-butyl group. All right, so like I said, this is too bulky to react with the aldehyde, so instead it will stop at the aldehyde and not overshoot all the way to the primary alcohol. All right, so let's take a look at some examples. And we'll practice this using an example problem. So let's say I have this compound. Where I've got a ketone and I've got a carboxylic acid. And my goal is to convert this to a product where the carboxylic acid is reduced to an aldehyde. Well, as we saw in the previous video, one way of doing this is to react this with BH3THF, and this will selectively reduce the carboxylic acid group. So this would work. It would leave the ketone alone. And then if we wanted to, we could then get to the aldehyde using something like PCC. The main downside to this is PCC still uses chromium-6. It's pretty nasty stuff. So a workaround now is to react this with SOCl2, convert it to the acid halide, so this would exclusively convert this OH group into a Cl group. And then, whoops, I forgot my double bonds in there. And then if we wanted to convert this to an aldehyde, what we could do is treat this with our special new reagent. That's the lithium triterbutoxy aluminum hydride. So LIALOTBU3H. And this avoids the use of the chromium-6 reagent. So this avoids a lot of the environmental and health concerns associated with that reagent. All right, the next one I wanted to look at is how these react with carbon nucleophiles. Okay. And with carbon nucleophiles, there's actually two main ones. The one we're really familiar with is a Grignard reagent. And so as you can imagine, if we have a Grignard reagent with an acid halide, I'll just use methyl magnesium bromide, whoops. It could attack in once, and it would give us something resembling a ketone, right? However, it can't stop here. In fact, let me change the colors here. We know that Grignards will attack into ketones as well. So instead, the Grignard reagent will add in uncontrollably, and you'll end up with a tertiary alcohol after you quench with water. So it's really hard to stop at a ketone, and just like we saw before, if we can't stop at the ketone, one trick is to use a bulkier reagent, and that's exactly what this next reagent is. It's bulkier. It's called a Gilman reagent. Some people just call this an organocuprate rather than using the name of the chemist that studied it, or published it, I should say. All right, and an organocuprate is kind of unique. We have two carbon-based groups bonded to copper, and this copper is essentially associated with lithium as well. So in this case, the R group is the nucleophile. Just like we saw in the reaction with Grignard reagents. And in this case, this whole thing is a lot more bulky, which means if you react this with something like an acid halide, what you can do is you can actually get one of these R groups to add in, but it will stop at that ketone. It's too bulky to add again. Which is kind of neat. All right, there's one last trick I wanted to show you. And this actually was something I've let slide a little bit, but I've noted a handful of times. And that is doing SN2 reactions with Grignard reagents is not allowed. But with Gilman reagents, it is. So I'll show you what I mean by that. Is prior in the year, I saw a lot of people do things like this where they said, hey, I've got a Grignard reagent. I've got an alkyl halide. Why can't this Grignard reagent do a backside attack and do an SN2 reaction? Instead, what we get is a mess of products. And this is due to a variety of reasons, one of which is we have a competition with E2 chemistry, right? So even though it's unhindered, it's such a strong base, this Grignard reagent, it'll do a fair amount of E2 chemistry as well. However, if you switch it up and you use a Gilman reagent, meaning the organocuprate, you can actually get an SN2 reaction to occur where you can swap out that bromine for a new R group. So one of these R groups over here will swap off, and you can actually do an SN2 reaction and alkylate. So Gilman reagents can be used for SN2 style alkylation. So even though this isn't directly related to the carbonyl chemistry we're covering now, it is a useful synthetic trick as we start doing synthetic problems later on. All right, so that's where we're going to stop now. When we come back, what we're going to do is we're going to look at anhydrides.